Okay, this is going to be the video for the second half of chapter 16. There's a couple things to cover here. One we've seen before and one will be new. So the first thing we're going to talk about is actually a review from earlier. We talked about this back in chapter 6. And that's how if you have a distribution of data, and this is going to be true now for random variables, true, if you multiply every element in that, then that has an effect on both the measures of center and spread. But if you're adding or subtracting, it only affects measures of center. It doesn't, spread is unaffected. So the best way to see that is, I'm just going to bring something from earlier. If, let's say we had a data set of some kind, and it had a middle value of 30 and 20 was over here and 40 was over here, and we did some kind of transformation where we're multiplying everything by 3. So if we did that, then that means this 20 would become 20 times 3 is 60. 30 would become 30 times 3, which is 90, right? Just make sure my screen is still live. Yep, okay. And then 40 times 3 would be 120. So the distribution would have two things happen to it, right? The measure, the center, the measure of center, like a mean or an expected value, would definitely be multiplied by 3. But also the measure of spread, the standard deviation, would also be tripled, right? So the takeaway here is that multiply affects everything. Okay. Now let's take another case. Let's say we had that same distribution, 30 in the middle, 20 down here, 40 up here. But now the transformation is that we're going to add 30 to everything. Okay, so the 20, if you added 30, would become 50. And 30, if you added 30, would become 60. And the 40, if you added 30, would become 70. And so what happened now is that, yes, the mean is affected. That we have to add 30 to, but the spread didn't change, right? So adding or subtracting has no effect on the spread. But does affect individual values, right? It does affect like the mean or any individual value. But things like standard deviation and IQR, right, those things would not be affected by that. And so that means, let's say that I had something like this. Let's say I did both at the same time. So I had some distribution here. And let's say, for example, that the middle value here was 30 and the standard deviation was 5. Okay. And then I'm going to do a transformation on this. And the transformation is going to be, I have some new thing, and it's going to be the old thing times 3, but also add 30. So I'm going to do both these things. I'm going to multiply by 3, but add 30. So that will form a new distribution, right? And this has some new mean and some new standard deviation. Okay, so what we're saying is the new mean will be equal to the old mean times 3 plus the 30, because the multiply and the add affect means. But the new standard deviation will only be 3 times the old standard deviation. We don't do the plus 30 because the plus 30 doesn't affect the standard deviation, only the shifting does. All right, so we've seen that idea before with data, and it turns out that that's also true here when we're talking about random variables. Okay, so just to practice that before we move on to the other part here that'll be more new, let's quickly try required practice problem number 3. So pause the video, give this a try, see if you can see what's being asked here. All right, so here's what is happening. We've got some things. I'll do a pictorial diagram of what's happening here. We have some variable x here, which has a mean of 10 and a standard deviation of 2. That's what they're saying here. And we want to find something new. And what we're doing to make the new thing is we're taking 3 times whatever x is, right? So we're multiplying by 3. All right, so that's going to give me a new mean and a new standard deviation. Okay, so the new mean will be 3 times the old mean, right? Because we're multiplying by 3, and multiply affects everything. So that would just be 3 times 10, which would be 30. Okay, the new standard deviation is also affected by that multiply. So 3 times the standard deviation of the old, and so it would be 3 times the 2, and so therefore 6. So this would be 6, and this would be 30 if you multiply everything by 3. Okay, and in the second part there, they're saying, all right, I have some distribution which we're calling y, and it's got a mean of 20 and a standard deviation of 5. And we're going to transform it. We're going to transform it by adding 6 to all the y's. All right, so we've got a new distribution over here. And it has a mean and a standard deviation. Mean new, standard deviation new. They asked us to find those. So the mean new would be the old mean plus the 6, right? So that would be our old mean of 20 plus 6 would turn out to be 26, right? But the standard deviation new will just be equal to the standard deviation old, because adding has no effect on measures of spread, and so it would still be 5. So while this would shift up here to 26, the standard deviation would still be 5 because all we did is shifted everything over 6. All right, so that's the idea there. Okay, if I switch back to the notes here, the next thing we're going to do is actually something in the practice packet. So we'll stick with the practice packet, and we're going to work on a simulation for something that right now we don't know how to do with probability, but we'll know by the end of the lesson. Okay, to save time and money, many single people decide to try something called speed dating. This is way back in the past, before internet and Tinder and all these other sorts of things, okay? So let's say we have a speed dating event. What happened was you got men and women who were interested in dating in the same place. They had the women sit in a circle, and then they had men sit directly across from them. Each started out sitting in couples, one man across from one woman. And then they spent about 5 minutes talking to each other, see if they hit it off. If they hit it off, they could exchange phone numbers, and then a bell would ring, and then all the men would get up and shift one chair over, so that now they're paired up slightly differently. So, and they kept doing this in 5-minute increments until they got back to the original chair. So at the end of the day, every man and every woman had met. Okay, and again, this was back in the days when we're only talking here about heterosexual couples. There's a lot more things going on, but this is just restricted to that. Okay, suppose the height of males could be represented by a random variable m of male speed daters, and they're normally distributed. So men have an average of 68 inches height with a standard deviation of 4. Okay, but women are also normally, their heights are normally distributed with a mean of 64.5 inches, standard deviation of 3. What's the probability that if I select a random female and a random male, that the female will be taller than the male? Okay, so we could kind of simulate just doing that once. Let's do this real quick. If you have your calculator with you, well, you need it for this. Seed your random number generator by typing some sort of random number in and then storing it. Remember the store button, math, and then probability menu, and then the random. That goes a certain number of spots into your internally stored random digit table. Okay, and then what we're going to do is simulate one man. Okay, so we're going to use the random normal feature. So if you go math, over here probability, and you scroll down here where it says random normal. Below random integer, there's a random normal. This allows you to get a random number from a normal distribution, and what you have to tell it first is the mean. So since we're going to simulate a man, we're going to put 68 in there, because they said that the average man was 68 inches tall, and then a comma, and then we'll put 4 for the standard deviation. And then we'll close the parentheses and hit enter. And that means we're going to get a simulated man's height. I'll round to the nearest tenth, 60.4 inches. And when you do this, of course, you'll get a different number, right? Because this is random. Okay, then I would like to simulate having a female. From their distribution measure where the mean is 64.5 and standard deviation is 3. So we'll go back to random normal, probability menu, type in 64.5 for the mean, comma, which is above the 7 key, 3, and then close parentheses, and that's simulating a woman. So in this case, I had 65.0 inches tall woman. Okay, and then is it true that the man is taller than the woman? In my case, yes. I had a 65-inch tall woman and a 60.4-inch tall man, so that my woman was taller. Maybe yours is the other way around, where the man was taller than the woman. So to kind of see how that might work, maybe what we could do is let's define a new variable. I'm going to call it D for the difference. And we're going to define it specifically to be the man's height minus the woman's height. So in my case, it was 60.4 minus 65. 60.4 minus 65. And so mine was negative 4.6 because in my inches. And the reason mine's negative is because my man happened to be shorter than my woman, right? Yours might be positive because yours is the other way around. Okay, so what we're going to do to figure out what this probability is roughly is we're going to simulate a speed dating event with 100 men and 100 women randomly assigned by our calculator. And then we're going to have the calculator determine what these differences are. And we're just going to count up how many times they're negative out of 100. And that'll tell us the probability, the percentage chance of that happening. So I'm going to walk you through this process of doing this with a simulation. Okay? All right. So first thing is, I'll ask you to load up list 1 with your men. So what we're going to do is this. We're going to type this in the calculator. We're going to use random norm, and we're going to use the men's value, 68.5, comma 4. But then we're going to put another comma and then put 100, because that'll simulate 100 men at a time. But instead of seeing it on the screen, I'm going to store that result in list 1. So it ends up in list 1. So let me clear my lists. So second mem plus or 4 to get rid of that. And then I'm going to do this. I'm going to say math probability, go down here to random norm, and then click 68, comma 4, comma 100 to simulate 100 men's heights. Close parentheses, then go press the store button above the on key, and then go second 1 to store that in list 1. And when you hit enter now, it'll take a little while, and then it'll show something on the screen. And if I go look at list 1 right now, it's got 100 men's heights listed, random men's heights out of a normal distribution. In fact, just to show you that, if I were to do you don't need to do this, but if I were to just turn on a scatter plot and make it a histogram and look at list 1, my simulated heights, sure enough, are a normal distribution, and let me put a trace on there. The center is somewhere in the 67 to 67-ish range, so 68, around 68, because that's where this is distributed, and the standard deviation, sure enough, is around 4. Okay, all right, so I actually don't need to have that plot turned on. Let me turn that back off. All right. So now we're going to do the same thing to simulate women. So for that, you will say random norm. Women's mean is 64.5, standard deviation 3. We'll simulate 100 women and store their results into list 2. So if you can work on that, we're going to go math, over here to the probability menu, down to random normal. And then we'll go 64.5. which is the standard deviation for the women, comma 3, standard deviation. Sorry, this is mean. 64.5 is mean, standard deviation. And then comma 100 to get 100 values. Close parentheses, store that, second 2 to store it in list 2, and then hit enter. Okay, now if I go look at my lists, I've got a separate list for the women. And since I'm interested in the differences, now what I'm going to do is I'm going to make list 3 equal to list 1 minus list 2 to calculate the differences. So I can scroll over here to list 3, make sure it's blank, highlight the name, and then put second 1 minus second 2 to simulate all those differences. So in these couples, like this 3 that I have here, 3.4, means the man is 3.4 inches taller, but this negative 1.5 means the man is 1.5 inches shorter, therefore the woman is taller. And so if I want to figure out what my simulated percentage chance is of having the woman be taller, I just need to count up how many of these 100 differences are negative. To make it easier to count, I'll show you how to sort these columns from lowest to highest on list 3 so that we get the most negative to the most positive. The way you do that is go back to the stat menu, but then scroll down one to sort A. That's ascending sort. Click it, and then we have to tell it which list to sort on, which is list 3. So second 3. And then since I want list 2 and list 1 to come along for the ride, I'm going to put comma, second 1, comma, second 2. What that's saying, if I close the parentheses and hit enter, is to sort based on the values in list 3, but keep lists 1 and 2 with list 3. So if you hit enter, it'll say done. And now when I go back and look at the table, I can see that it's sorted from the most negative to the most positive. So I had a couple here in my case where the man was 12.7 inches shorter than the woman, right? And then if I scroll down here, at some point, it's going to cross into positive territory where the man is taller. Right? So if I want to figure out how many of these where the women is taller, I just need to count up the number of negatives. But rather than count it, there's an easy way to do it. If this is in order, you can put your cursor on the last negative one and see how that says L324 for mine. Yours might be different. That means that's the 24th entry. So that means 24 out of 100. So in my case, my simulated probability of having D be negative, which is the probability of having woman taller, is that happened in 24 out of 100 cases, right? So my probability is 24%, and yours would vary around a little bit, right? Because everything's random. Okay. All right, so we could solve this problem by doing a simulation, because right now we don't know how to calculate this directly as a probability. But now we want to talk about how would you calculate this using probability rules instead of having to resort to simulating. Okay, so if we go back to the notes, this last topic for chapter 26 is how do we not just transform one distribution, but what if we're combining two different distributions that each have their own variation? Okay, so if the typical male height is 68 inches and the typical male height is 64.5 inches, the way to think of it is this. I'm just going to actually jump to the screen that summarizes it. Okay, if you have a distribution of males, okay, where this is 68 inches high and this is 64.5 inches high, and the standard deviation for males is 4 and 3 for that, you can define a new random variable D for the difference, maybe as male minus female, and write out the algebra for that. D is equal to M minus F. The means do just what you would expect. They follow the algebra. So the mean of the differences is going to end up being the mean of the males minus the mean of the females. So if the males are 68 inches tall on average, and the females are 64.5, if you subtract those two, 68 minus 64.5, you get 3.5 inches, right? So on average, the difference in heights in the couple are going to be 3.5. The men's going to be 3.5 inches taller. And in fact, if I were to do one variable stats on my list 3 of the differences, I just really quickly do that. You don't have to do this. I'm going to take off the probabilities so I don't have a frequency list. Then the mean should be around 3.5. Now mine's 3.1 because this is random simulation. But you know, if I did this with many, even more than 100, this would be very close to the theoretical difference of 3.5. The question is, so what that's saying is this difference is 3.5 inches. Now, the trickier part is how do I combine these two sources of variation to get this standard deviation here? Now that's a little trickier, right? So it's the way to think of it intuitively is this. If you know that the men's and women's heights are independent, okay? In other words, if you were to graph them, the male height versus the female height, there'd be no association. You couldn't do this if you had an association, but if you have this case where there's no association, and typically you don't have to check it, it'll tell you that it's independent in the problem, then that means the men's heights are varying, say, let's imagine we're picturing it horizontally, and the women's heights are varying vertically because they have no effect on each other because they're at right angles. It turns out that whenever you either add or subtract the two random variables, the new random variable's distance will vary as the hypotenuse of these other two. So you have to take this side squared plus this side squared to get the hypotenuse squared. So this is sometimes referred to as the Pythagorean theorem of statistics. Okay, and what that means is that if I want to find the standard deviation of the difference over here, I have to take the standard deviation of the men and add the standard deviation squared of the women. But it's not the standard deviations add. The standard deviations themselves don't add. It's the standard deviations squared add. So it's actually the variances, which are standard deviation squared. So the variance total, which is standard deviation squared, will be the variance from one source of variation plus the variance from the other source of variation. And it doesn't matter if we're adding or subtracting these numbers, right? The fact that I have variation for males and I have variation for females, it doesn't matter that this is subtract. Every time I add more variation, I always get more total variation, right? So the variance for the difference is equal to the variance for the men plus the variance for the females, which in this case, the variance is the standard deviation squared, right? So 4 squared, 3 squared for the females. And so the standard deviation squared here, and that means the standard deviation is the square root of the sum of those squares, the hypotenuse length, which turns out to be 5 inches, right? All right. So that's in fact how we would solve the speed dating problem without having to do a simulation. Let's go back and we'll do it again. This is in the packet. This is another page to fill in. So I want to show you what I would write if I was writing this up. I wouldn't do a simulation. I would do it using the rules for combining means and variances. I like to write out little pictures. So I would say, okay, we have the men. They have some variation centered at 68, standard deviation 4. And then we have the women, and they have variation centered at 34, 64.5, standard deviation 3. And so when I combine them, because I'm interested in the difference, I'm going to define that as the males minus the females. That has a mean, which I'm going to call the mean of the differences, and a standard deviation of the differences. All right. So the first thing I do is I write out the algebra, right? The algebra is that the difference is just the men's minus the women's. I'm just arbitrarily choosing that order. And then for the means, it's going to exactly follow the algebra. The mean of the difference is equal to the mean for the men minus the mean for the women. This is exactly what I would write. So that'd be 68 minus 64.5, which is 3.5 inches are the units. Okay, but for the standard deviation, it would be the variance. The variance of the difference is equal to the variance. The first source of variation is the men, and then I'm adding, because variances always go up if I add more sources of variation for the females. So that would be that standard deviation squared for the difference is equal to the standard deviation squared of the men plus the standard deviation squared of the women, right? Which is going to be 4 squared plus 3 squared. And therefore, the standard deviation here is the square root of 4 squared plus 3 squared, which turns out to be 5 inches. Okay, now we haven't actually answered the probability question yet. So what is the probability? Well, now I can work with this distribution. So let me go down lower here, and I'll copy it again. Let me change colors. Okay, now we know that if I draw a normal distribution for the differences have an average difference of 3.5 inches with a standard deviation of 5 inches. And I'm interested to know when the women are taller. Since this was defined as men minus women, it'll be that women is taller whenever this difference is negative. So somewhere over here below 3.5 is 0, a difference of 0. And anything over here would be where the woman is taller. Okay, so to find that, that's just a probability under a normal curve. So the probability that the woman is taller, we can just use our normal CDF function from earlier in the class, right? We can say that's equal to normal. I wish my thing would quit bugging up here. Normal CDF from negative infinity, so negative 999, let's say, for the lower bound, up to 0 as the upper bound. If the mean is 3.5 and the standard deviation is 5. And so we would do that in a calculator with normal CDF. So let's get back to the command line. Second variables, normal CDF from negative infinity to 0 on a normal distribution that's centered at 3.5 with a standard deviation of 5. turns out to be 0.24196. This is the exact probability that that will happen. And our simulated probability when I ran it was about 24%, which is very close. So you may have gotten 20, 22, 27, somewhere in that range because it was a simulation, but this is the exact probability. Okay, so that's how we combine more than one distribution variation. Okay, let's go back to the notes for a second. Okay, to summarize, there's two things you can do with distributions. If you have one distribution, you can transform that, right, by adding or multiplying things, right? And the rule is that the mean is affected by both the multiply and the add and subtract, but standard deviation or variance or IQR or any measure of spread are only affected by the multiply, but not by the adding and subtract, okay? But if we're combining multiple sources that each have their own variation and they're independent, you write out the algebra, the means follow the algebra, and the variance is always add. Okay? All right. Then just to wrap this up, go ahead and give required practice packet number 5 a problem a try. So go ahead and read that, give it a try, pause the video, and when you're done, unpause it, and then I'll show you the answer. Okay, so for this one, it says we have a house in Hawaii. That's lucky. Which has very little variation in outside temperature throughout the year, but we pay an electric bill and a gas bill at the house. Random variations month to month cause both of these bills to go up and down, and the costs are independent of each other. That's important because we can't do the variance calculation otherwise. If the electric bill, let's use E for electric bill, costs a mean of $40 with a standard deviation of 12, and the gas bill costs a mean of $25 with a standard deviation of $8, what is the mean and standard deviation of the total cost? So let's use T for total cost, and I'll just define that to be the sum of the two. Total means we want to add that. So that means we'll have a mean for the total costs and a standard deviation for the total costs. All right, so let's write the algebra out. Its T is E plus G using random variables. Therefore, the mean of the total is equal to the mean of the electric bill plus the mean of the gas bill. So that's going to be 40 plus 25, or 65. And the units here would be dollars. So to include the units, we'd use the dollar sign. Okay, mean is easy. Okay, for the variability, we know the variance total has to equal the variance for the electric bill plus the variance for the gas bill. And variance is standard deviation squared. So the standard deviation squared. Okay, so that means that the standard deviation here is 12. So 12 squared gives us the variance. And then this is 8 squared. So the standard deviation for the total bill is the square root of 12 squared plus 8 squared, right, which turns out to be rounded to the nearest cent, $14.42. So then we could answer other questions, like if we knew that this was approximately randomly or normally distributed, we haven't been told that in this problem, but if we knew that, we could make a normal distribution and say, find out what percentage of the time is the bill over $80 or over $100 or something like that. Okay. All right, so that should wrap up the rest of chapter 16 here. Now, one last thing to talk about. Okay, this total here, that we don't have to be limited to just two sources of variation. Let's say we had an egg carton, okay, carton of eggs. Okay, and so there's a dozen eggs in here, right? There's 6 eggs plus the carton itself. And maybe we knew that that the empty carton had a certain weight. We had its mean and standard deviation. And then we knew that an egg varied with a certain weight and standard deviation. And there were 12 of these eggs in here. 12 eggs worth of these things. If I wanted to know what the mean and standard deviation of the weight of the entire carton would be, well, the total weight would be the empty carton weight. So plus, let me use G for an egg. Actually, you know what? Let me use C. I'll use C for the carton and E for the egg. So we would have one carton plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 eggs, right? So there'd be 12 of these eggs here. And every one of those is its own source of variation. So if you wanted to find the mean, you would take the mean of the carton plus the mean of this egg plus the mean of this egg and so on, which this would end up being 12 means of the eggs, right? And when we did the variances, it would be the variance total. So the standard deviation squared is the standard deviation of the carton squared plus a standard deviation for an egg squared plus another standard deviation for another egg plus another standard deviation for another egg, and that would happen 12 times. So we would end up being able to make this formula: 12 standard deviations of eggs. So if you write out the algebra as far as adding and subtracting, right, it doesn't matter how many terms you have, not just two. You could have 13 different sources of variation, the carton plus the 12 eggs, and you sum a new variance in for every one of those eggs along with the carton to get the total variance. So very flexible technique here. All right, that'll be it for the video here.